Hello everyone. Welcome to the ILTA Physics Problem Solving Lecture. Today we're going to work on a problem regarding collisions on a two-dimensional plane. As you can see in the diagram on the right, this involves two balls colliding and moving off in different directions across a flat surface. To analyze collisions and the resulting motion on a two-dimensional plane, we calculate the motion in the x-axis direction and the y-axis direction separately, and then superimpose them. This approach means we decompose the object's motion into horizontal and vertical components, analyze each one independently, and finally recombine them back into the overall motion on the plane. In today's session, we will solve problems divided into two main categories: collisions on a 2D plane and explosions on a 2D plane. Now let's briefly summarize the theoretical method for analyzing collision motion on a 2D plane. I'll quickly go over how to analyze the collision of objects on a two-dimensional surface. This is the case as shown in the diagram where two objects on a plane hit each other and move away in different directions. The law of conservation of momentum still holds true in two-dimensional collisions. In other words, the total momentum before the collision and the total momentum after the collision are always equal. However, how we calculate the total momentum in a 2D collision is a bit different. The total momentum is the sum of the momenta of each object, but it's not just a simple addition. It's calculated as a vector sum. I repeat, it is a vector sum, not just a regular sum. By vector sum, I mean we add the x components together and the y components together separately. Since we said the total momentum before and after the collision are equal, this means, as you can see in the equation, the total momentum of the x components before the collision equals the total momentum of the x components after the collision. In the same way, the total momentum of the y components before and after the collision will also be equal. Let me explain this further using equations. Let's look at the motion of the two colliding balls in the diagram again. For convenience, let's focus on the velocity of the first ball after the collision. The velocity moving toward the northeast after the impact can be divided into an x component and a y component. We can do the exact same thing for the velocity of the second ball after the collision, breaking it down into x and y components. Now let's calculate the momentum for the x-axis. To keep things simple, we will use a prime symbol to represent velocity after the collision. The x component of the momentum before the collision is calculated by multiplying each object's mass by its initial velocity in the x direction. Similarly, the total x component of the momentum after the collision is calculated by multiplying each object's mass by its final velocity in the x direction. We can find the momentum for the y-axis before and after the collision using the same method. I've explained this at length to help you understand, but the bottom line is this. Divide the velocities of the objects before and after the collision into x and y components, and then apply the law of conservation of momentum to each axis separately. All right, let's summarize the steps for analyzing 2D collision motion. First, define the system, which includes the objects where no external forces are acting. Then draw diagrams of the system before and after the collision. The diagram in the top right is a great example of a before and after diagram. Next, set up a coordinate system to express the motion of the objects mathematically. Generally, the Cartesian coordinate system consisting of horizontal and vertical lines, that is, the x-axis and y-axis, is most commonly used. Finally, as I just explained, calculate the conservation of momentum for the x component and the y component separately. Now let's solve a problem regarding a collision on a 2D plane. Problem 38 is a classic 2D collision problem. It describes two pieces of clay with different masses moving diagonally on a plane, colliding, and then moving together as a single mass. Since it's a collision on a 2D plane, the law of conservation of momentum applies, and because they move as one piece after colliding, it's an inelastic collision. Let's apply the problem-solving steps we discussed earlier. First, I'll define the system where no external forces act. In this case, we can just define the entire setup, including the two moving clay pieces, as the system. Second, let's draw a diagram of the motion before and after the collision as described in the problem. The diagram on the right shows the before and after states. Please note that the two clay pieces are stuck together after the collision. To analyze this motion, a Cartesian coordinate system with an x-axis and a y-axis is appropriate. Actually, once you get used to solving problems, these steps will become second nature. Now, it's time for the step where we quantitatively analyze the motion the problem is asking about. As explained before, we divide the velocity into x and y components and calculate them by applying the law of conservation of momentum immediately. First, let's calculate the momentum by dividing the velocities of the objects before the collision into x and y components. The formula for momentum is mass times velocity. Object 1's velocity before the collision only has an x component and no y component. Therefore, the y component for object 1 before the collision is 0. Now, let's look at the velocity of object 2 before the collision. Since object 2 is moving diagonally, we can easily express it using trigonometric ratios. One thing to watch out for is that the direction of motion for object 2 has a negative value. This is because, if you look at the x component, it's moving to the left and downward. Please make sure to pay close attention to the signs when calculating. If these equations aren't quite clear yet, feel free to pause the lecture for a moment and think it through until you're comfortable. Okay, now let's calculate the momentum after the collision. Since it's an inelastic collision and they stick together, the momentum is the sum of the two masses multiplied by the final velocity. As you can see in the after diagram on the right, the final velocity we're looking for can also be split into x and y components. Now let's apply the law of conservation of momentum to the x and y directions separately. Based on the principle that momentum before and after is equal, the x component of the final velocity is 0.28 meters per second. Using the same method, the y component of the final velocity is minus 0.3 meters per second. Again, keep in mind that since the y component of the velocity is downward, it takes a negative value. I'll say it once more. When analyzing motion, make sure to use the correct signs in your calculations. Up to this point, we've gone through the decomposition and analysis stages of the 2D collision. Now, let's calculate the final step of recombining the results. This is the same problem continued. We previously found the x velocity and y velocity of the combined clay mass after the collision. Now we'll use the Pythagorean theorem and trigonometric relationships to calculate the actual magnitude and direction of the object's velocity after the collision. According to the Pythagorean theorem, the magnitude of the velocity after the collision is calculated as 0.411 meters per second. Using trigonometric properties, the direction of the velocity after the collision is minus 46.9 degrees. As shown in the diagram on the right, this points diagonally downward from the positive x-axis. We just solved a typical 2D collision problem together. To recap, divide the velocities before and after the collision into x and y components and apply the law of conservation of momentum to each one independently. Let's take a look at the next steps in the following slide. Problem 39 is an explosion problem where a firecracker, which was originally one piece, explodes and splits into three pieces flying in different directions. Please pause the video for a moment, read the problem, and make sure you understand it. An explosion can be analyzed as the reverse process of a collision. Therefore, momentum is conserved before and after the explosion. And since it was one single piece before the explosion, it can be analyzed like an inelastic collision. However, when solving these, keep in mind that in most explosion cases, the object is at rest beforehand, meaning its velocity is zero. Therefore, the total momentum before the explosion is simply zero, and calculating the sum of the masses doesn't change that. Since the problem doesn't give us the masses at all, let's assume the mass of the smaller piece is m. That would make the mass of the third piece 2m. And this is also motion on a 2D plane. We must calculate the momentum and velocity by splitting them into x and y components. The figure on the right is the before and after diagram of the explosion described in the problem. Before the explosion, it is a single object at rest. So the total momentum before the explosion, which is total mass times velocity, is zero. If we look at the after diagram, we can see that the first and second pieces fly south and west, respectively, according to the problem description. For the third piece we're asking about, we can logically guess that it will fly in roughly the opposite direction toward the northeast. Now let's calculate this quantitatively. We calculate the velocities of the three pieces flying off after the explosion by dividing them into x and y components. First, let's consider the x and y components of the velocity for the first piece. The first piece is flying south. In our coordinate system, that's the negative y direction. So the x component of its velocity is 0, and the y component is minus 20 meters per second. The reason the y velocity is negative is that the object is moving in the negative y direction. Be careful with the signs. In the same way, because the second piece is flying in the negative x direction, its x and y velocity components are minus 20 meters per second and 0, respectively. Make sure you clearly understand why one is negative and the other is 0. For the third piece we're looking for, the mass is 2 meters and the velocity is an unknown variable. Let's move on to the next step in the following slide. Now that we've split each object's velocity into x and y components, we can calculate the momentum for each axis as follows. Let's continue by applying the law of conservation of momentum before and after the explosion. According to the law of conservation of momentum, the x and y components of the momentum before and after the explosion must be equal. Calculating this, the x component of the third piece's velocity after the explosion is 10 meters per second, and the y component is also 10 meters per second. This completes the stage of decomposing the motion and analyzing each part. Now for the final step, recombining the final velocity. Since we have the velocity for each direction, we can calculate the overall magnitude of the velocity using the Pythagorean theorem, which comes out to 14.1 meters per second. The direction or the angle of the final velocity is 45 degrees based on trigonometric ratios. As you can see for both 2D collision and explosion problems, you simply decompose the velocities of the moving objects into x and y components and apply the law of conservation of momentum to each axis separately. That's it for today's lecture. You all did a great job. See you next time.